Hey everyone, welcome to the next part on the antiderivative rules, indefinite and definite integrals. We're going to be focusing on the last success criteria D, where we want to evaluate definite integrals that look something like this using the Fundamental Theorem of Calculus Part 2. So just as retrieval practice, why don't we remember what the second Fundamental Theorem of Calculus is, or the Part 2 anyway. If I have a definite integral from a to b of a function, what does this equal to? So why don't you pause and fill that in, or remember, or say it out loud. Okay, so just recall, we learned that this is equal to the capital F, or the antiderivative function of b minus capital F of a. So this idea is going to be very important for us in terms of evaluating definite integrals, such as this. So let's take a moment and look at a previous lesson. In that lesson, we were asked to find the displacement of some runner that runs along this path at a position function of t squared plus 1 from time 1 to 3. And so we can see that the displacement is just the final position minus the initial position of 11 minus 3, which gives us a difference in 8 meters. Now we also learned that we can also find displacement as an accumulation of the velocity or the rate function. So the accumulation from 1 to 3 is the area under the curve, which also gives us 8. So when we set these two equal to each other because they're equivalent, we came up with this expression, or this equation, where the accumulation from 1 to 3 is equal to the net change of the position. So S of 3 minus S of 1. And then we generalized it to form the Fundamental Theorem of Calculus Part 2, which stated that if you have some rate function or a derivative function, and then you went from the intervals a to b, the accumulation of that is equal to the antiderivative of the endpoint minus the antiderivative of the initial point. So let's take the concepts in this previous lesson and apply it to this current lesson. So imagine this time we have a runner. Instead of being given the position function, we're given just the velocity function for 0 to 4. So here it is, where v of t is measured in meters per second and t is measured in seconds. Now we want to find the runner's displacement from time t equals 1 to t equals 3 seconds. And so what we can do is use the second fundamental theorem of calculus to find that answer. So why don't we set that up? We know that the displacement is going to be, the displacement from time t equals 1 to 3 seconds is 1 to 3 of your velocity function dt. And in previous lessons, we were able to evaluate this just by looking at the graph of the area under the curve. But in this lesson, we want to be able to solve this by just looking at the function. So why don't we rewrite this as 1 to 3 of the velocity function, which is actually 2t plus 1 dt. So what I'm going to do is I'm going to cover up this velocity graph here. All right, so let's solve this definite integral. Let's see if we can do that. Okay, so looking at the fundamental theorem of calculus part 2, we see that when we have a definite integral like this, we can say that this is equal to this expression on the right side, the antiderivative of b minus antiderivative of a. So in other words, what this means is if I can find the antiderivative function, I can plug in b and then subtract it by when I plug in a. Okay, so let's find the antiderivative function. So when I find the antiderivative function, it's going to be, okay, so 2t plus 1. The antiderivative of 2t is t squared, and the antiderivative of plus 1 is just plus t. And then as always, we don't want to forget the plus c. So I just found my antiderivative function, right? And then what do I need to do? I need to plug in b and an a, which is 3 and 1, and then subtract the difference. So how we notate that is we do something like this. We put a line after the antiderivative, and then we put 3 and 1 as our upper and lower bound. This is just to indicate that we're going to plug 3 and 1 into the antiderivative and then subtract the 2. Okay, so when we do that, we'll end up getting 3 squared plus 3 plus c minus 1 squared plus 1 plus c. And then I'll go over here and say that is equal to 9 plus 3 plus c minus 1 plus 1 plus c. So that's just 12 plus c minus 2 plus c. And then if I distribute that, I'll get 12 plus c minus 2 minus c. The c's cancel out, and then I'm left with 10. And I should probably put equal sign on each of these. Okay, so now why don't we verify that this displacement of 10 is correct by looking at the accumulation of the velocity graph. All right, so if I look at the graph of v of t and find the area under that curve from 1 to 3 and find this area, I can break it up into a rectangle and a triangle. So the rectangle is a 2 by 3, so that's 6 inside the rectangle, and then a 2 by 4, that's 8, and then cut that in half, so that's 4. So if I add these up together, I get a total area of 10, which matches my second the Fundamental Theorem of Calculus Part 2. So really cool. All right, so I intentionally left this middle part blank because I wanted to fill it in with some new notation here. So this part right here, that's what I want to fill into this spot. So essentially, when we take, in a general case, the definite integral from a to b of some function dx, what we first do is find the antiderivative function, f of x plus c, and then we just put a line at the end and say the upper bound b and a, and so that's just what we do for notation. So that's just what this means, and then after that you just plug in the b minus a, and then you'd get this expression, and then solve for your final answer. All right, so I want to point you to something that's pretty interesting about this problem. Did you notice that we never figured out what the original function was exactly, right? Because remember, what this plus c represents is all kinds of cases for what the original position function could be, right? This c could have been 1, 2, 3, 4, 5, pi. It could have been any point right there. But in the end, we didn't need to know what that c value is to actually get an answer. So let me show you what this means conceptually in a graph. All right, so here is a graph, t squared plus t plus c. It's the same antiderivative function here. And then take a look at the displacement when I turn it on. So here we go. As you can see, the displacement from the point 3 to 1, 3 minus 1, you get an answer of 10, which matches our answer, right, for the displacement, which is really cool. Okay, so now I was saying this c ends up canceling out and not mattering, even though we don't know what the original function is, right? So why don't you look at this slider here. If I move this c value, here's 1, here's 2, here's 3. What does the c essentially do? It makes the graph just shift up or down. We call it a vertical shift, if you remember your transformation rules, right? But notice what's happening to the displacement. The value of the displacement, no matter where I put the c value, what the c value is the same. The displacement, because the displacement just means the change in the y values of the antiderivative function. So it doesn't matter whether the function shifts up or down. The change in the change in y value, the displacement, is always going to be the same. So that's why the c value doesn't matter, because we're not dealing with what are the exact y values of the antiderivative function. We're actually dealing with what is the change in the y values, and that's why the c doesn't matter for definite integrals.